This is the lecturette for sections 19.1 and 19.2, the beginning of our examination of entropy and full thermodynamic control of chemical reactivity. We start by talking about entropy and the three laws of thermodynamics, one of which you've already encountered. The overall control of reactions comes from two broad areas. One is thermodynamics, which examines the relative stability of different molecules, the energy of the molecules, whether or not the products or the reactants are lower in energy. And the other is kinetics. Kinetics is the study of the rate of reactions. So for a reaction to actually happen, it must be thermodynamically favored as well as kinetically favored. That is, the products must be more stable than the reactants, or the final state must be more stable than the initial state, and it must actually occur fast enough that it can be observed. So for thermodynamic control of reactions, there are two parts of this. One is enthalpy, which mainly has to do with bond energies. And the idea is that forming stronger bonds favors reactions, and molecules with strong bonds are more stable. In enthalpy, remember, enthalpy change is delta H. So delta H is part of what controls reactions, but not entirely. The other thing that controls reactions is entropy and entropy change. Entropy gets a symbol S, and entropy change is delta S. And there's a lot of different ways of thinking and talking about entropy, and what we'll be doing is talking about it as randomness or, in particular, freedom of movement. And we'll do this in a little more detail in a second. But reactions that increase randomness or increase freedom of movement are favored. And those involve an increase in entropy. And in particular, it's easy to examine reactions or to predict reactions that will be favored from entropy by those that increase the amount of gas that's present, because gases have a great degree of freedom of movement, and they will be things that form gases are generally favored from an entropy point of view. Let's look at the laws of thermodynamics. At least the first one we talked about is the first law of thermodynamics, which we did when we talked about thermochemistry, and that is that energy is conserved. So that's all we're going to say about that for now. We're now going to talk about the second law of thermodynamics. And in the second law of thermodynamics, it says that all physical and chemical changes that occur will occur such that at least some energy disperses. And disperses means spread out. So energy will disperse. The total concentrated or organized energy, that means a lot of energy in one place, in the universe decreases. So whenever anything happens, the total concentrated energy in the universe decreases and becomes more dispersed. And so the diffuse or disorganized energy increases. So all spontaneous processes, all processes that actually occur, involve energy going from more concentrated form to a more dispersed form. The total entropy of the universe always increases whenever any spontaneous reactions. For us, the way to think about entropy in terms of chemical systems is that in chemical systems, entropy is viewed as the freedom of movement of molecules and atoms. That's the way we kind of visualize it for chemical systems. So entropy is the measure of dissipated energy within the system. It's the symbol S, capital S, and the units are joules per Kelvin. The second law of thermodynamics says that all changes involve an increase in entropy of the universe, and the entropy of the universe can be segmented into the entropy of the system that we're using. So that's usually the reaction we're studying or talking about, and the surroundings. And the surroundings is the rest of the universe. And so the entropy change of the universe is the sum of those two things, and that has to be greater than zero for a reaction to be spontaneous, for the reaction to occur. Entropy is a measure of this dispersed energy, and so each chemical entity has a standard entropy, and it's usually tabulated in entropy units, joules per Kelvin, but on a molar basis. And so we're going to look at this this part of this table here, and there's a bigger one in your appendix for your book, or the date tables for your book. And so notice that two forms of carbon, diamond and graphite, both have very low entropies, but graphite has greater entropy than diamond does. Most solids, you'll notice, have relatively small entropies, particularly things like just standard metals. And when you go to liquids, they have somewhat larger entropies. So liquids have greater entropies than solids, and in general gases over here have greater entropies than do liquids. There are other factors that affect the overall entropy, overall magnitude of an entropy for a substance, and we'll look at those in a second. But it's important to note that the range in entropies for things is pretty broad. So potassium iodide is a solid, diamond's a solid, but they have very, very different entropies. So let's look at some trends in particular. First of all, we'll look at state, the state at which things exist in. So in gases, the molecules can move completely free of all the other molecules, so they're not constrained in any way of their movement. So these gases have the greatest freedom of movement. In liquids, what happens is the molecules can move past one another, but they can't move just anywhere they want because there are lots of other molecules close by that block their way. So they're somewhat free to move, but not completely free to move. And numerically, you can see that, and this is an example with bromine molecules. The element bromine, Br2, has an entropy of 245.5 joules per Kelvin in the gaseous state, but only 152 joules per Kelvin in the liquid state, showing that the liquid can't move as freely. In the solid state, molecules do move, but they can't move past one another. So they can rotate in place, but they can't move past one another. So it's much more constrained. So solids have the lowest entropy, gases have the highest entropy, and liquids are intermediate. Entropy of everything increases as temperature increases. So as temperature increases, entropy increases, even if the state does not change, even if there's no phase change. And that's because as temperature goes up, the thermal energy of the system increases, and molecules will just move around more. They'll be more free to move, and they'll move faster, and they'll disperse around a particular volume of space more so as the temperature goes up. So a tabulated entropy has to be for a particular temperature. Molecular size plays a role, and in general, larger molecules have greater entropy because they have more ways they can move. The molecules, the atoms inside the molecules can vibrate and move around, and the way they vibrate and move around increases with the more atoms they have. And so if you look at a series of hydrocarbons, methane is very small. It's only got one carbon and 4 hydrogens, and it has an entropy of 186 joules per Kelvin. Ethane, on the other hand, is a somewhat larger molecule, and it has a larger entropy. And propane is larger yet, and it has a larger entropy. Forces between particles in a solid, in particular, also play a role. If you look at the example of sodium fluoride and magnesium oxide, these involve ions that are roughly the same size. They're ionic compounds. But in the case of sodium fluoride, the charge on a sodium is +1. The charge on a fluoride is -1. And so that's a certain amount of ion-ion attraction here. The size of the charge on a magnesium is +2, and the size of the charge on an oxygen is -2, 2-. The ionic attractions between the magnesium and the oxygen ions is 4 times greater than the ionic attraction between the sodium and the fluoride, and because of that, the magnesium and oxygen ions have less freedom of movement because they're more tightly bound, and they have a lower entropy. So going back to our table, let's talk about where these numbers come from. We have all these numbers, and they're not entropy changes. They're actual entropies of compounds or elements. Let's talk about where they come from. The third law of thermodynamics says that any perfect solid at 0 degrees Kelvin, which can't be obtained, but at absolute zero, there's a substance has 0 entropy. And what happens is, as you take that solid and you heat it up, it starts vibrating, it starts moving a little more, and its entropy will increase with temperature. So entropy will increase with temperature until you reach the melting point. At the melting point, what happens is a phase change where the solid breaks down and becomes a liquid, and the entropy increases dramatically because now all of a sudden the molecules can move with respect to one another. And so at that temperature, the entropy goes up a great deal. Then you have a liquid, and the molecules can move around past one another. As the liquid is heated, the entropy still increases because the molecules can move past one another easier and to a greater extent as the temperature increases. The biggest change in entropy comes at vaporization. So when you take the liquid and break all those molecules apart from one another, that leads to a great increase in entropy as all of a sudden those molecules become free to move completely freely. And so that's when you get to the gas phase. And then the gas increases in entropy a little bit as the temperature goes up because the molecules can move to a greater extent. So we can look at this in a particular case for water, looking at water at some different temperatures in Kelvin. So as a solid, water increases a fair degree in terms of how much it's multiplied by, but a fairly small degree in terms of absolute numbers, going from 2 degrees to 38 degrees Kelvin. When you go up and get to the liquid phase at 273, which is where it melts at 0 degrees Celsius, the temperature, the entropy is significantly higher, and it goes up to a relatively modest extent as the liquid is heated up to the boiling point. But at the boiling point, the entropy goes up dramatically. Most of the entropy change totally happens when it boils and vaporizes, going from a liquid to a gas at that temperature. So these numbers here reflect going from here right up to there. And so by adding up all those entropy changes for each of those steps of heating up the liquid and the solid and the gas, depending on which phase you're in, and the entropy changes for the phase changes, one can arrive at the actual entropy that we have in those tables. We now move on to section 19.2, which is how we do calculations of entropy change. In general, the change for entropy is very much like the change for enthalpy. It's the change in that state of that property, entropy, between the products and the reactants. And so an entropy change is generally given by the sum of the entropies of the products, the final state, minus the sum of the entropies of the reactants, the initial state. So going from final minus initial gives you the change in entropy. If the system gets more random, more freedom of movement, then delta S is positive, and that favors the reaction. If the system gets more ordered, that's less freedom of movement, then delta S is negative, and that disfavors the reaction. And so what we're going to look at a special case of phase changes, and then we'll look at reactions in general, and also how to just eyeball and make estimates about whether entropy change will be positive or negative for systems. We'll look at phase changes first. For a phase change, the entropy is given by the Q, which is the heat exchanged during the phase change, divided by the temperature at which it happens. And so the heat exchange is actually the enthalpy change. So it's the delta H of the entropy change, a delta H of the enthalpy change for either melting or vaporizing, divided by the temperature at which it happens in Kelvin. And so we'll do a quick calculation here. We'll do a quick calculation here for the heat of fusion, that is melting of ice. So when ice melts from the solid state to the liquid state at 0 degrees Celsius, what is the entropy change? So delta S is given by the heat exchanged, and from the point of view of the delta H, energy has to be added to the system to melt, so that's a positive. So it's 6,000 joules per mole over the temperature at which it happens, and 0 degrees Celsius is 273.15 Kelvin, and so we divide that, and that gives us our entropy change. And our entropy change is 21.97 joules per Kelvin mole. And so determining the entropy change for a phase change is actually relatively simple. And that's a positive value, as you would expect, going from the solid to the liquid phase. I'll talk about calculating delta S for all other reactions. And this is similar to the way one calculates enthalpy change, delta H, using standard heats of formation. But in this case, we're going to use standard entropies. And so we're going to look at the reaction of propane with oxygen to make carbon dioxide and water. One caveat, one thing to be careful about is when you did this for enthalpy, the enthalpy of formations for elements in their natural states was 0, and that's not true for entropy. The entropies of elements in natural states are numbers just like everything else. So delta S, standard entropy change for this reaction, is going to equal the entropy change for the products, the entropies of the products, standard entropies of the products added up, minus the entropies of the reactants added up. So what we're going to do is we're going to take the product first. So we'll take 3 times the entropy change for CO2. The 3 is because there's 3 moles there. And for CO2, it's 213.7. I'm going to leave off all of the joules per Kelvin until we're done. Plus 4 times the entropy for liquid water, which is 69.9. I'm going to subtract from that the entropies of the reactants, the 1 propane and the 5 waters. So the entropy for propane is 269.9, and the 5 oxygens are 5 times 205.1. So we'll do the math on that. The products add up to 920.7 joules per Kelvin. And the reactants add up to 1,295.4 joules per Kelvin. And therefore, delta S for our reaction is equal to negative 374.7 joules per Kelvin. So remember that two things to be careful about is make sure you use the number of moles of each species when you do your calculation, and also remember that the values for elements in natural states are not equal to 0. In looking at reactions, you can often decide whether the entropy change will be positive or negative just by a quick eyeball look at them. Not always, but often. And the first thing to look for is that reactions that have an increase in the moles of gas present will lead to a positive entropy change, and reactions that have a decrease in the moles of gas will have a negative entropy change, because gases have large entropies. So in this first case, so we're going to look and see if we can predict the sign of delta S for these reactions. We have a solid going to make two gases. So in two ways is the freedom of movement increased here. You take one thing, you're breaking up into two things. And also taking a solid and breaking it up into gases. So that will definitely have a positive entropy change. Here you have two gases going to make one gas in a liquid. So the number of moles of gas is decreasing, so that will have a negative entropy change. Here you have two things. Go away. Here you have two species, two molecules going to make one molecule. So it's two things coming together to make one, which decreases the freedom of movement. And also 2 moles of gas goes to make 1 mole of gas. So that has a negative entropy change. Here you have 3 moles of gas going to make 4 moles of gas, so that'll have a positive entropy change. And here you have 2 moles of gas going to make 4 moles of gas, so that'll have a positive entropy change. So you can guess the, or estimate the, or predict the sign of entropy change fairly easily for reactions that involve gases. Another thing to look at is the effect of dissolution. And if you take, for example, sodium chloride, which is a solid, and dissolve it into water and make NaCl aqueous, at first glance it seems that the entropy change should be positive, because what happens is the solid sodium chloride has all these positive and negative ions in a regular array, so the entropy of the solid salt is very, very low, because the solid is in this very ordered array of ions. When it goes into the solution, they're all spread out, because all the ions can float around just completely randomly. And so you're taking the salt and you're spreading it out and allowing all those ions to go their own way. So from that point of view, it seems like the entropy should increase. And so if we look at the reaction of going from solid to aqueous sodium chloride, we say that that's true. The entropy change for that is 115.5 minus 72.1. And so the entropy change for dissolution of NaCl is equal to plus 43.4 joules per Kelvin. So it's a fairly large positive increase in entropy. So that follows what we were thinking about. However, if you look at the entropy change for sodium hydroxide, when solid sodium hydroxide dissolves into water, its entropy change is negative. It's negative 16.4 joules per Kelvin. So how is it that a solid, which is very ordered, dissolves, has much more greater freedom of movement? How does that end up to a negative entropy change? It has to do with the water molecules. When sodium hydroxide dissolves in water, the hydroxide in particular, hydrogen bonds with lots of other water molecules, and what happens is those water molecules can now no longer move as free as they used to. So the sodium and the hydroxide ions, those actually do have an increase in their movements. But when the hydroxide goes into water, it constrains many, many water molecules around it, and the water becomes less free to move. So the water's entropy decreases, and the overall system between the water and the sodium hydroxide, it overall has a negative entropy change. So the effect of dissolution is you can't predict. Some dissolution reactions lead to positive entropy changes, some lead to negative entropy changes. What we're going to do is we're going to look at the second law of thermodynamics again now that we have a better feel for entropy and what's happening. The second law of thermodynamics says that the total change in entropy between the system and the surroundings has to increase for the total, for the universe, if a system is going to be favored overall thermodynamically. And so we've talked now about the system. We know how to calculate or even just kind of eyeball guess the sign for entropy change for a system, but now we have to worry about the surroundings. The main thing that affects the surroundings when a reaction happens is the heat that is either given to the surroundings or absorbed from the surroundings, and what that does to the entropy of the surroundings as the surroundings get warmer or colder. For an exothermic system, heat transfers to the surroundings. Energy transfers out of the system into the surroundings. So the surroundings gain heat, and therefore the entropy of the surroundings goes up. Because now the surroundings have more energy, the molecules are moving more, the motions of the molecules in the surroundings has increased for an exothermic reaction. So for an exothermic reaction, delta S for the surroundings is positive. For an endothermic system, energy has to come from the surroundings into the system. And so therefore, the surroundings lose heat. The surroundings loses heat. Loses heat, who can tell? So delta S for the surroundings then decreases because the molecules can now move less because they've lost energy. And so therefore, the sign of entropy change for the surroundings for an endothermic reaction is negative. And so for our overall reaction, we can calculate the entropy change for the system itself, but now we also can calculate the entropy change for the surroundings based on how much heat the surroundings gains or loses. And the way that works is that the system has its own delta S, and we've talked about how to calculate that. The delta S for the surroundings is equal to minus delta H for the system. That is how much energy is coming into or out of the system, but from the perspective of the surroundings. So if the system is losing energy, delta H for the system is negative, but that means the surroundings is gaining energy. And therefore we change the sign of delta H for the system so that it's actually talking about the energy exchange for the surroundings. And you take that energy amount and divide it by the temperature at which the reaction happens, and that becomes delta S for the surroundings. And then you add that to the delta S of the system, and you get delta S for the universe. So let's look at an example of this. Let's calculate the entropy change for the universe for this particular system here. So let's start with delta S for the... so we have delta S tabulated here for the reaction, and we have delta H tabulated for the reaction. So delta S for the universe is equal to the delta S for the system plus delta S for the surroundings. So that's going to equal minus 351.6 joules per Kelvin, which is disfavors the reaction happening. But that's going to be plus negative. Now, there's something important to watch here. This is 752.2 kilojoules per mole, so we have to change that to joules. So it's negative the delta H. This is negative delta H for the reaction divided by the temperature. And so what we're doing is we're taking negative delta H, so it's 752 2,200 joules. Oh, and I forgot to say what temperature this is at. Let's say this is at 25 degrees Celsius. So that's going to be at 298.15 Kelvin. So we're going to have minus 351.6 joules per Kelvin for the system. And then this is going to be plus a negative negative, so that's going to be plus. If you do that out, it's 752. 2,523 joules per Kelvin. So when we add those together, we come out with 2,171 plus 2,171 joules per Kelvin. Because this is positive, because delta S for the universe is positive, the reaction is going to be favored. Now let's look at this. So our delta S for the reaction is 2,171.3. I left off the 0.3. So the reaction is what we call product favored. Product favored means that it's favored to make products because it's favored to go towards the product side because delta S for the universe will increase if that happens. From an entropy point of view, delta S for the system, the reaction is not favored by entropy because the entropy change for the system was negative. So this reaction is not favored by entropy, which makes sense because it's got 4 moles of gas on the left, 1 mole of gas on the right. And so from an entropy point of view, the reaction doesn't really want to happen, the entropy of the system itself. But the reaction is favored by enthalpy because the enthalpy is giving energy to the surroundings, which increases the enthalpy of the surroundings. And so at this temperature, the reaction, this is a kind of logic that you need to kind of get used to thinking about. The reaction is not favored by entropy. The reaction is favored by enthalpy. Overall, the reaction is favored. So the reaction is controlled by the thing that's making it do what it's doing. It is favored, and the thing that's favoring it is enthalpy. So at this temperature, the reaction is controlled by enthalpy. It's enthalpy controlled because it's doing what enthalpy wants it to do. Enthalpy wants it to go. Entropy wants it to not go. It is going. Therefore, enthalpy is the thing that's winning out. And that ends our section 19.2.